Okay, we'll go ahead and get started. So again, thank you so much for joining us today. I did want to cover a few housekeeping items before we jump into the main part of the content. So we will be presenting today on metal injection molding, supported by a Freeform Injection Molding process here at Nexa and our xMOLD resin. Um, if you run into any sort of technical difficulties, feel free to shoot us a message into the chat, audio or video difficulties, anything like that, please reach out and let us know, and we will try to help you to the best of our ability. My best piece of advice, if you do run into any sort of lagging video or spotty audio or something like that, is to actually leave the webinar and jump back in. It's not the most intuitive process, but it is typically the most effective with this Zoom platform. Other than that, we will not be taking questions along the way, but we will do a Q&A session at the very end. So please open up your Q&A box, make sure to enter your questions as we're presenting so you don't forget them, and we'll address as many as we can with the remaining time. If there's any sort of critical questions we weren't able to address, we'll be sure to try and reach out after the fact to make sure that you get your answer. And with that, I would love to introduce our two speakers for today. We have Lasse from Nexa, who you guys have probably seen several times. He's our director of Freeform Injection Molding here, and not only incredibly knowledgeable about Freeform Injection Molding and injection molding in general, but an all-around good guy and a lot of fun to learn from. So he'll be a good sport for today. And joining us is Sebastian from Fraunhofer, to talk specifically about the metal injection molding process with the xMOLD resin, which I think is really an incredible application that expands what you can do with our technology as well as the xMOLD resin. So for today, here's what we're going to be covering. So we'll talk about who is Fraunhofer, so you guys have a little bit of perspective of Sebastian and his background. We'll be able to address what challenge we're trying to solve with turning to freeform injection molding for MIM. We'll also address what solution we implemented. Basically, how did we get there? What was that process like? And how did we end up with beautiful metal injection molded parts? And then Sebastian's really going to be able to share as well, what did they get out of it? Why did they turn to freeform injection molding in the first place for this activity? And how are they going to leverage this moving forward? Before we open up for Q&A, and we'll answer all the questions you might have. And with that, I will turn it over to Sebastian.
Thank you, Lewis, for the nice introduction here. I hope you can hear me perfectly well. So before I head over to Lasse again, we'll have a little forth and back in the beginning of the presentation. Just very few words about my background, or basically my employer, Fraunhofer. I'm working at one of the many institutes of the Fraunhofer Society called Fraunhofer IFAM. You can see some of the data here. We have two main focuses in our institute. One is adhesive bonding technology and surfaces, so a lot of glue development and how to apply glues basically, but also how to treat surfaces, and a lot of polymer development, which of course plays a quite important role also in FIM and also metal injection molding. But I am employed in the area of shaping and function materials as a head of the department powder technology. And in this department, which is located in Bremen, one of the locations that we have some work where we are active. My group has a strong background focusing on metal powders and how to make parts from metal powders. So one of the long-standing technologies that we have looked into for over 30 years is metal injection molding, which I will explain in 2 slides about, and then also how this freeform injection molding option is basically introduced there. And this shows already that we are strongly focusing on additive manufacturing these days, not just the freeform injection molding, also a little laser-based powder bed fusion, but mainly metal binder jetting is one of our focus areas. And so in this field, you can see this institute has a lot of activities also in other areas that are listed here, and some information on our overall budgets over the last years. I won't go into any details there, but I think head over to Lasse for some more interesting details on the technology that we're here to talk about.
Well, thanks a lot, Sebastian, Lewis, for providing this. I'm very happy to be here today. I'll be at the Form next week, where we'll also be talking a lot about freeform injection molding. And for those of you who are not familiar with the freeform injection molding process, it's basically a hybrid between conventional additive manufacturing and injection molding. Today, the focus is going to be on metal injection molding. But those of you keeping up to date with what Nex is up to will know that we have also been dabbling in high performance thermoplastics, silicones, composite materials, ceramics, and we try to make it plain that this solution we have is a very versatile hand tool. The process itself, of course, starts in the CAD environment with the design of a part, which we then convert into the design of a mold, which is the inverse of the part, of course. Designing is done in whatever CAD software you have at your disposal. It's not a very complex process because at the start of the day, a FIM tool is basically a block of metal that encases the part, and it contains an inlet for the material to flow into, and it contains at least one outlet so we can get the air out of the mold. So the first thing you're going to notice when you start working with a freeform injection molding is that the design process of the injection molding tools is going to be a lot more simple in the prototyping stage. Once we have developed the design of the tool and sliced it according to standard 3D printing practices, we start the printing. And printing is done, not surprisingly, on Nexa 3D printers. We've got the LSPC system, which is our resin printing platform. That platform comprises 3 different printers, the SIP Pro, and the NXE 400. From a printing point of view, they are the same in the sense that they convert liquid resin into solid objects. And what we see here on slide 2, picture 2, sorry, is the printing of 3 pretty large molds in a complex lattice structure. Step number 3 is the injection of material into the printed mold. We use standard injection mold machines. We use standard injection moldable materials like the xMOLD feedstocks that Sebastian is going to talk about a little later. And then as the 4th step, we provide the injection molder with 2 alternative demolding patterns. For simple parts and for non-stick materials, we offer the opportunity of simply splitting tools apart like you would with a conventional tool. But for more complex designs and materials that may stick to the mold or may be fragile, like metal feedstocks, for instance, we offer the opportunity to dissolve a part. And the solubility of xMOLD is really one of the key enablers that allow us to manage very complex part designs with very simple tools. You will find in this slide, which I guess will be broadcast after this webinar, a link to a video which shows the process for conventional polymer injection molding. But the 4-step process that I've just described is essentially what you're going to see in the video. So I'm not going to spend my time or your time here watching the video. You can pursue it afterwards at your leisure. So with that, I'll hand the speaker baton back to Sebastian for a review of how this process actually interfaces with metal injection molding.
Right. So for those who are of you who are not familiar with the MIM process, MIM stands for metal injection molding. So injection molding is the key shaping aspect here. And you can see the steps here outlined from top to bottom on the left side. So you end up with a metal part. That's clear. So it's a metal fabrication technology, but you start with a powder. And the powder is mixed with a binder, as we call it. So it's a mixture of polymer and usually some kind of wax, surfactants can be quite complex, but often it's at least two or three components, and those are then mixed in a mixer at an elevated temperature where the binder is melts and the powder can be worked into the binder, so that you get a thermoplastic material that contains a very high share of metal powder. And this we call the feedstock. And you can also see in this depiction here some time frames that you see how long these steps roughly take, which will be important in a sec. So this mixing is done in about a couple of hours usually. So you have this material that you can directly go onto a very typical commercial injection molding machine, perhaps with a hardened screw, but otherwise completely normal injection molding machine, and just shape your part according to the tool that you have attached to the injection unit. And then, of course, this tool usually is opened up, ejected, or the parts, the green part, as we call it, is ejected, which is still powder and binder mixture. And then we have to remove this binder, which is usually a two-step process. It can be done as shown here, either by dissolving some parts of the binder system, or it can be a chemical reaction, which is used, for example, for the cutter mold feedstock that we are showing later, where a chemical reaction decomposes a part of the binder system, but enough, just not all of it, just enough to get it further placed into a furnace, where the rest of the binder is thermally decomposed, and then you usually go directly to the sintering temperature, and then you consolidate your part by basically fusing together the powder particles. While this is done, they shrink and eliminate any porosity so that you receive a shrinked version of this injected part, but usually with a density of around 95 to 100%, depending on the material. And you can see some of this takes hours, seconds, the binding about half a day to a day, the sintering a day. But we have this component here. Also, you have to click, sorry, those. Where the component that we are focusing on now is the tool. Because this has to be, of course, constructed, which is not as simple as with a film mold, because you have a lot of components that you need. It has to be open. You have to integrate cooling, sometimes sensors. It's can be quite complex, and the manufacturing then of all these components of a tool that takes about usually weeks, sometimes months. Depends also on who does it. Do it yourself? Do you have a tool manufacturing in-house, or do you outsource that for a tool manufacturer? And usually when you have the mold for the first time, you test it and you see some aspects are not perfect, so you have to rework, you have to adapt the tool, and this all again takes some days or weeks. So this is really time consuming to get the mold for your production. Now, where the film comes into play, the freeform injection is the next, you can see it here. So basically, we don't have this complex tool, but we have a very easy tool, basically a base mold, as we call it. So you have either a rectangular or a cylindrical opening in this tool where you can place this printed shape inside. This printed shape here, in this case, as Lasse explained, is an insert, a mold. So it's a block that has some cavity and some inlet, some outlet that you can see here. It's simplified just with the inlet with a sprue, and then if you print this and put it into your base mold, you can see that there's a line, the opening of the mold, which is the sprue, the gate, and there the feedstock comes in and fills basically everything, if you do it correctly, that was a cavity inside your printed mold, and then you can eject this as a block that is filled with the feedstock, and then you can remove this mold. As Lasse mentioned, the most important aspect is here the dissolution of this material, which gives you the opportunity to have any kind of undercuts that you would not be simply able to eject, because just geometrically not possible. And then you can see this is really done inside in a matter of hours to a day, So basically, the solution of the mold is the longest aspect of this this chain here if you introduce it. So having a base mold ready, where you know the outer shape of your insert that you have to print, the mold that you have to print and put into this base mold, you can really get going very fast and can get generating prototypes very fast compared to when you construct and build a complete mold for it out of metal and the way it's usually done. And with that, I head over again to Lasse for the next aspect we talk about.
Thanks a bunch. And before I dive into this slide, Mark Morrison kindly asked the question, is the mold ever reusable or is it always a single use? Well, we try to reuse them whenever we can. The fact that molds can be dissolved does not mean that we have to dissolve them. The reason why we usually end up in a dissolving scenario is that most of the parts we get to work with are fairly complex. Now, one example, and this is just a tool that I always have on my desk, is our impeller. Those of you occasionally active on LinkedIn will have seen the impeller as a part, but this is a tool creating the part, and it consists of one side, which is very simple and utterly reusable, and then it consists of one side, which I wouldn't want to reuse, because if I try to reuse it, I basically break my part. So I can reuse this part, but this part goes into the dissolving. Of course, that requires that my material doesn't stick to my mold and that my material is not fragile, but for most feedstocks, including the metal injection mold feedstocks from BASF, the Kata molds we are using for this case study, you can do a partial mold separation. If your part is simple enough, you can also separate the mold completely, and then you can reuse. So I hope this answered the question, Mark. Otherwise, please elaborate. Herod Gliss has also asked a question that I will just do right now. Do you use the AM mode during the MIM sintering step? No. The key difference between freeform injection molding and what you would see other printed tooling manufacturers do is that we get rid of the mold before we start sintering. And that means we don't get problems with carbon on the surface of the part. We don't get problems with contamination of the green body. But this is much more into the expertise of Sebastian than me. I just read a couple of studies. Okay. Thanks for the questions. Diving into this slide, we've tried to describe the problem we're trying to solve in general terms. I guess all of you know 3D printing. It's a great prototyping technology. It allows us to do a lot of stuff in the development phase that would normally require extensive simulations or similar. It makes it easy for us to test products ideas in practice. Most of you will also be familiar with injection molding, which is a great manufacturing technology once you've defined your design and once you want to start scaling up. But the problem is, at least from our point of view, that there is no easy connection between the world of 3D printing and the world of injection molding. You can use 3D printing for prototyping. If you want to scale into manufacturing, you need to jump into injection molding for a lot of cases. And if you do so, you will want to be able to test your ideas with injection molded parts. But since injection molding tools are expensive, this is usually something that you do at a very late stage in your development. And that actually constrains your learning in a typical product development process. So that's why we introduced freeform injection molding as that crossover that starts in 3D printing and ends up in injection molding, with the abilities of incorporating the entire range of injection moldable materials and the design freedom from 3D printing retained. So that's the problem we're trying to solve, get from prototype into production with a better decision quality, with a better test domain. And for freeform injection molding in the metal injection molding domain, some of the problems that Sebastian have already mentioned are related to the complex materials, metal feedstocks, but also to the quality of those materials. And this is some of the things that I know that Sebastian will be talking about a little later. So next slide, please. I have been working with Glenn Mason from Wilson Sporting Goods for quite a while, and he is a great guy for many things, including to condense the key impacts of freeform injection molding in the world of Wilson Sporting Goods. And one of the key experiences that he has won is that even with the best simulation designs, even with a fully integrated injection molding tool factory, you will be limited in the amount of time you can reduce in a development process, because essentially you need complex machinery, you need highly trained operators, you need precision time. And problems with the metal tool is also that when you start cutting into metal, you are basically freezing your design. Nobody wants to start reworking a metal tool. And one of the reasons why I think metal injection molding is interesting is because after the injection molding process, you've got that secondary step of sintering. You also learn about your parts in the sintering step, and that certainly increases the risk that you'll have to rework your tool. So what we try to change in the equation of injection molding is to make the mold cavity itself more flexible and a lot cheaper to manufacture in the prototyping stage. And if we look at the next slide, we can see that the key impact from printing injection molding cavities instead of cutting them in metal is that we reduce the cost of failure. A cavity like the one I show here costs perhaps 15 to 20 euro in total to make and fill and demold, whereas a complex metal tool can run into the thousands of US dollars or even more. And that means that the point of injection molding is the point where you really start accumulating cost in your product development process. By 3D printing your cavities, you reduce the time to fail, which means you get improved decision quality, and you definitely also reduce the cost to fail. One of the key quotes from Glenn Mason is that as soon as he gets the first part out of a tool, he knows whether his idea is good or not. And it really sucks to have developed and manufactured a metal tool for a wrong idea, which costs even more sometimes than a great idea. So Glenn Mason's key take home from implementing freeform injection molding is that it allows him to iterate faster and cheaper, while at the same time reducing the cost of failure. And if you look at a process like metal injection molding, where you have a debinding step and a sintering step after your injection molding, the costs of failure, the costs of getting the tool wrong, are going to be even higher than the costs experienced by Mr. Mason. Next slide, please. The key use cases that we have been focusing on when we develop freeform injection molding are three main cases where we have a combination of high mix and low volume. Of course, we have a first design and development phase. This is where all additive manufacturing technologies have an important role to play. But since we are focusing on the injection molding, which is the manufacturing technology, we can also follow the product into the market. If you've defined a good recipe for injection molding, a small volume of parts like 50 for a test, you've also defined a production protocol for making 50 custom fit objects. Could be for a specific customer, could be for a specific application, could be a specific adaptation of a high rating part. And that means that if you implement freeform injection molding in your product development, you also automatically get a low volume manufacturing added to your prototyping domain. This low volume manufacturing, of course, is useful when you start scaling up and adapting your product. And it's also extremely useful for the spare parts management later in your product lifecycle, when you want to start scaling down your product because the demand is declining, and where you may not want to maintain an expensive injection molding tool. So 3 core use cases: prototyping / product development, customization and adaptations, and spare parts on demand. I think we've got 2 questions One, which is thin film allow complex and potentially fine featured green parts. Is there any guidance about sag or deformation during sintering? I will comfortably leave that to you, Sebastian. And the second one, what are the advantages of using this process using a Nexa printer versus a Triton mold jet process that builds the molten green part at the same time? Well, Sebastian, I guess you'll have some key insight there as well, but from my point of view, the most
Guys, if you can
important.
hold the questions for the end, that'd be
Okay,
great.
sure. Okay, thanks, Louis. Over to Sebastian for the next one.
Yeah, so perhaps some of the aspects of these questions will also be answered during the next slides. So, so what are we doing with the freeform injection molding? So, of course, we are a research and development organization or an institute of an organization. So we, of course, want to understand processes and bring them as far as possible into the market, so that sensible things can be done with these processes, I would say. And in that respect, we help different aspects of the or we look at different aspects of the whole development of these processes. And in that respect, for the freeform injection molding, one of the most important things that we have come to realize, which may not be surprising, but is actually the design and of the molds, the inserts, the molds, because actually how they behave during the process is the most important aspect that we have come to realize that we have to look into. And so designing and that they can be printed, of course, in a design that is printable, because also, of course, there are some limitations for each process, and that also goes for the DLP process that produces the mold. Of course, we are looking into the injection molding side of things regarding the materials. So can we use the standard feedstocks, commercially available feedstocks, or can we adapt some things that improve also on that? I mean, one of the key aspects that also perhaps answers the second question a little. Of course, if you're an injection molding, or you work in a metal injection molding company, and you can use your production material to make prototypes, because you know how it debinds, how it sinters. That is, of course, a key advantage that can be taken. And that, of course, well, if you have to adjust the feedstocks to improve things, then you, of course, may not have the production material in the same manner. And then it's then the question, if you cannot use another technology, of course, becomes perhaps more important. But this is at least an option that we look into. So what do we have to do to make these standard materials applicable for the freeform injection molding? Of course, we look at the demolding, which is a very crucial step, and the debinding and sintering. Of course, this is done as the materials are again the same way processed in the typical MIM process. So this is actually not something that changes things. I'll get into that a little later. And of course, we evaluate these results. We do internal R&D. We have a lot of responsibility also as an institute to educate students. So we of course have bachelor thesis, master thesis, doctoral degrees that we have people working on here. So of course, understanding these aspects within student works is an important aspect, including publishing and dissemination. We collaborate with other institutes, but also a lot, of course, and targetedly so with industry that are interested in this technology. And so these customers of ours are, of course, what we want to help to make use of this technology. So next slide, please. I'm sorry. So one of the main test cases that you probably have seen when you wanted to, or when you were made aware of that webinar, is this bracket that you can see here as not as the part itself, but already the design of the mold that has been printed. In that case, Lasse has printed this basically at his facilities. And you can see that it's a two-part mold, but that has different reasons here. And it's actually not a part that is designed for MIM. So this is also an important factor here, because MIM rules still apply. And this is some takeaway that you can already have here, although later I will come back to this. So it is not a perfect MIM part because it has very long flow paths. So if you inject it, you can see the injection at the bottom here and in the back a little. So, but the feedstock has to flow for a very long time. And now one key difference between these printed molds and metal molds is that you cannot really heat them. It's the same as a metal mold. A metal mold has some internal channels where you can heat with thermostat, because you can pump water or any liquids through these channels and then heat the mold. So you can directly influence the way that your feedstock will flow or stop flowing during the injection. And this is something that is one of the key differences. So as the plastic insert cannot be heated in the same manner, you have lower flow lengths that you can achieve. And this was one of the aspects that why we chose this part. We wanted to see if this very long flow path part can be made at all with this Freeform Injection Molding tool. And we used this commercial feedstock that was given to us by BASF, Catamold 17.4pH Evo feedstock. So that's just for you to as a reference here. And on the next slide, we see the results. Of course, not everything worked perfectly. So this is basically the best part that we got out. But we saw that we do have some difficulties with filling the mold due to the reasons I just explained. So the mold is basically cold compared to what a metal mold would have been set to in terms of temperature when you would have used that. So the filling is not as easy. And also we have a design of our base mold that is not perfect for this kind of large molds, because we cannot really apply the clamping pressure to hold the mold close. So we cannot, due to that, we cannot inject with a very high pressure or which leads to a high speed of the feedstock to fill the cavity. And as it's cold, we would actually have to inject faster than we would do with a metal mold. And this wasn't possible perfectly well due to the space mold concept. And that's why we didn't have a perfect result. But as you can see, we achieved the filling, and we could also demold the part where we had some issues, but it worked quite well. Debind and sinter afterwards without issues. So basically, you can see that you have a typical metal part. Sinter density was same as a usual MIM part, and we do have some distortion, but of course, as I said, this is not a MIM part, so it's also not designed for sintering, because in sintering you have to watch for other details than just for when you have to look for when you just inject a material like plastic injection molding. So different aspects that come into play here as well, but I think it's nice to see that it worked still, and we got this nice part. And of course, we did some other stuff in the past, and the next slide shows a little of the first works that we did when we didn't even have the printer yet at our facility. So these molds were supplied by Adifab at that time. So we did some very initial tests with this nut and bolt design. We tried some watch cases where we saw some of the issues with removing this material by dissolution, because one aspect that you have to take into account, which I will go into a little more detail on the next slide, is that this material, when you dissolve it, it swells slightly. And now this feedstock that you have, this metal powder filled polymer, basically, this is quite rigid, so it's prone to breaking quite easily. So when this material that you remove from the mold swells a little, during this demolding, then you have the risk that you see at the bottom right, that you may crack a part, especially when you have basically some internal material that when it expands will basically go press to the outside of the part. So I hope you can understand that. That's why, for example, in the lower bottom right, you can see this crack on this mold watch case at the top due to this slight swelling. But as I said, we also have some work here with students, and we recently had a very nice bachelor thesis work here that you can see on the next slide. Basically, at least a very small part of it, and so we dove more into depth into this aspect of how to design the mold to successfully get parts out of it. And we were asking questions like, how thick does a wall have to be? Does it even, is this the factor, or where do we have to look? And we one of the main takeaways that we realized was that this swelling of the mold itself is the issue that you have to look into, and you have to compensate it, but not just by avoiding it. So not just, like removing the outside part of the mold and just dissolving the inside, or other way around, but you have to basically create the mold in a way that anything that swells and may induce a force on your part is counteracted by the other side of the mold. So basically, you have to find a balance of the forces that can occur due to the swelling. And this is the part where it really gets interesting, because we realized how to better design molds, how to approach this. And as you can see in the lower middle picture, of course, we try to minimize the amount of material that we have to remove, because simply put, I mean, this material costs money, and the more you have to dissolve, the more material you waste, basically. And of course, it takes longer. So cutting down process time by shortening the demolding step, and cutting down costs by trying to make the parts as small as possible that you have to demold. We also, in the same step, basically created adapters where we adjusted the molds. So we have this base mold, as you can see on the right side, the metal part, but then we have inserts that are also kind of adapters where we can easily put these smaller molds. So for each part, we designed also this black base mold, which is a typical resin for DLP or SLA printing, which can be reused. Well, they didn't break, so I would say you can reuse them indefinitely, but definitely a lot of times. And then when you just place in these small parts that you have to dissolve, you actually do a lot of saving time and money in the process. So this was a very interesting work that led to a lot of insights on our side into the design of the molds. And with that, I'm basically finishing with the examples of the parts on this slide. So what we try to see is these wall thicknesses that we can make, and you can see sometimes these parts break. So there is some kind of a minimal wall thickness. It's not. It's very dependent on the feedstock, and we didn't investigate different feedstocks here, but we saw that you can go, for example, for this cutter mold in this case, down to about 1 millimeter wall thickness, freestanding, so to say. But as you can see on the right side on the photo, where we have sintered parts, well, there are some parts that have even some issues that you can see with cracks. So it's not that everything that we do always works perfectly. So there is still a learning that we have to do, but we can, as you can see more in the back, we could really make a lot of parts that were perfectly fine. And the interesting thing is that really all the features that you have inside your printed mold, they translate perfectly to the feedstock. And this is good to know and very important to know, because if you skip to the next slide. Oh, sorry. Yeah. This takes basically or relates to the second point. The surface quality that you have inside your printed part, this translates to the metal. So any stairs, let's say, from printing, any waves, any roughnesses, they will definitely translate into the metal part. So of course you have different quality aspects than with a tool made from traditional processes where you can, you know, like polish the surfaces and everything and have very super super surface quality. So of course there is a limit there. So you will not be able to have everything that you can have with the metal mold, but you can have different aspects as well. So very interesting still. And from a metal side, it's the same. So density, microstructure, the composition. So as Lasse also said, we don't have any residues from the mold. So after sintering, the microstructure and the density are there, same as MIM parts. So it's just the other properties like the surface quality that directly depends here on the printed mold and that you have to take into account. Of course, there are some surfaces also from your printed part that are better than others. So if the surfaces that are directly on the bottom of the printer, let's say, or on the bottom of your bath, they are usually the highest quality surfaces compared to upstanding walls or even tilted walls. So if you have some features of the part that you want to have a very good surface quality, you have to think about how to place this mold inside the printer, or how to design the mold that you get the good surface quality at places where you want to have it, if it's possible. I mean, there are some limitations there, but this has to be considered when talking about quality here. Next slide, please. I hope I'm not running out of time. Yeah. So as I said in the beginning, or as very early on, the laws of MIM, so to say, they still apply. So what's not good for a part for MIM, because you have to sinter it when you have transitions from very thin to very thick walls, because this is always where you have the highest potential of distortion during sintering due to some bending, some forces that will distort the whole part. Gate positioning and also the dimensioning of the gate is important, because you want to be able to fill the mold properly. And of course, if the gate is too narrow, you lose a lot of pressure. You cannot really inject the material with a high speed. Or when you position the mold in a stupid way, let's say, you may get injection fronts that combine at a certain place where you get some cold weld lines. So so there are a lot of things that come into play, and this of course can also be supported by mold filling simulations that are state of the art, that you can use also to simulate the filling behavior of your printed mold if you are not sure how the flow fronts behave, for example, and how the flow path is. And if you want to avoid these weld seams, as they're named here, you can integrate also simulation for the mold filling. Next slide, please. So so is it what's the impact of the freeform injection molding? Of course, it doesn't replace anything. So it usually adds to the well, let's say to the possibilities that you have. So as Lasse said, one aspect is that you can shorten design cycles. So usually when you have to rework these molds and then these traditional molds, this is so time consuming. So you can rework these freeform injection molds very quickly, as we already showed you. Thus, these iteration steps, they're not as costly as when you do this with a traditional mold. So you can actually basically do the design cycle completely before you even start investing into a mold. I mean, you can parallelize this as well to even save more time if you're, let's say, sure that you achieve where you want to get. But I think this requires a lot of knowledge and experience. But of course, it may be able to reduce waste. Of course, you have different kind of waste that you produce, but it may not be as much. And perhaps you can, as you save some costs, do even more projects. So there are some advantages that are definitely can definitely be seen. Next slide, please. And so where do we want to go forward in the future? Of course, as I mentioned several times, we're a research institution. So of course, we want to drive these developments that I have just highlighted here very briefly in the future. New materials is just basically what we're always interested in to develop, and perhaps some of the materials that may, give some advantages in the freeform injection or freeform metal injection molding, may be also interesting for the injection molding itself. As I said, you can use the production material, but of course, if you can, for example, demold or during demolding do the debinding of the feedstock, the chemical debinding, this would save time. Of course, there are water debindable binders on the market, and those may be also combined and debinded during the demolding where you dissolve the mold. So this is stuff that is definitely interesting, where you can then save a certain step that you would have to to do otherwise. Of course, we are also interested in how manufacturing, of course, changes in the future, and how where the freeform metal injection molding may also support stuff like mass customization, this virtual warehousing, and spare parts on demand. All the things that additive manufacturing addresses in potentially. And that's, of course, leading to new business models in the long run. So this is perspectives that we see. And of course, all this requires people who are able to work with these technologies. And of course, as a research organization, we also see that we provide training and education to people. As I mentioned before, we're doing a lot of our work also in student work. So this will definitely produce people that will be also able to bring this directly into the companies. Yeah, and with this, I'm not sure. Yeah, I think exactly. So we are actually at the end of our slides and would be moving on to Q&A. But I head over to Louis, I guess.
Thank you guys so much. I will jump in real quick and start passing through. We've got several good ones coming through. This is a good one too that I hope we have made clear, but it definitely bears emphasis, and that is, can this technology be used for molding metals only, or would it be possible to mold polymers as well?
Yeah, of course. I mean, it was first developed for polymers, so that's actually why I also saw it first. I think it was on a Compamate in Düsseldorf when I saw it first, and where it showed a plastic molded part, and then I said, yeah, why not, bring this into the metal injection molding that I know. And of course, there were already some works going on into this direction, but it also, we have colleagues in Dresden from IKTS, another Fraunhofer Institute, that use this for ceramic injection molding, for example. And we have different, let's say, molding based technologies that may also be interesting, not just injection molding, but casting, for example, like with materials that can just, like cast without any pressure into a mold and then solidify. And so there are a lot of options how to use this material. Anything that you basically can let flow into a mold is potentially something that you can think about how applying this freeform injection molding concept to.
Thank you, Sebastian. Yeah, I do think it's important to point this is, an opportunity to leverage injection molding for some complex stuff like ceramics and the like. So I think that just speaks to the extreme versatility of the material.
Definitely.
Okay. And so getting back to specifically metal injection molding, I'll start with this question, Sebastian, to you. Since FIM allows for complex and potentially fine-featured green parts, do you have any guidance about sag or deformation during sintering? Well,
this is basically independent on the freeform injection, because after having made a green part, it doesn't depend on whether it was made by a traditional tool or the freeform injection molding. So this has to be considered when designing the part for a sintering-based technology. And this is definitely something that you have to consider. And there are a growing number of also simulation-based approaches to really, do the sintering simulation. We are also involved in a couple of those. So this is actually something, as I said, more or less independent on the process. Of course, some processes, they may have a different powder distribution, different distribution of porosity or some thermal stress that may also be lead to some other form of distortion. But in principle, these features and how they behave during sintering and how you have to stage a part during sintering, or do you have to use live setters or preformed setters, stuff like this may also be where you can, achieve production-like quality if you consider using some traditional means to prevent, for example, distortion of complex parts that are used in the metal injection molding industry for years. So, yeah, not directly related to the shaping process, but a general issue you have to look into.
Good advice. Lasse, I think this will be a good question for you. If not, feel free to redirect to Sebastian. But what are the advantages of using this process with the Nexa printer versus the tritone mold jet process that builds the mold and green part at the same time?
I think Sebastian actually provided part of the answer to that question in his just concluded remark. When you design injection molded parts, the injection molding is only one part of the equation. Getting the debinding and sintering right, getting the mold flow right, is what is a real key concern for injection molders. And that means if you're using an additive manufacturing technology for prototyping of MIM parts, you're not answering the basic question, can it be molded? And for metal injection molding also, can it afterwards be sintered to a good result? I think, Sebastian, you can probably elaborate, but when you talk about injection molding, the key prototyping step is to injection mold.
I think actually, when I think about a manufacturer and how they set up their manufacturing processes and the environment, if you already are in metal injection molding and you have your materials that you know how to process the debinding, the sintering, there's a general hurdle to implement further sintering-based technologies. It doesn't matter if it's the mold jet or if it's metal binder jetting, because what you would have to do is you would have to run these materials, these parts that you create with these other technologies differently, different debinding, different sintering temperatures, dwelling times, to perhaps adapt the design because they shrink differently, not anisotropic. Of course, that's not the case for mold jet, but maybe for other processes. So you get a lot of different questions that you have to answer, and you cannot simply let basically these prototype or let's say low volume series parts run along with your production that you're doing on a daily basis. And this is, I think, an advantage that is potentially there for the freeform injection molding, because if you can really use your production feedstock material that you sinter every day, and you can just throw in basically parts, prototypes, just a couple of parts that you want to put on the table of your customer to get a project. Like this is an advantage. And if you have to make these from other processes, then you always have the question, does this really then relate to a MIM process, if that's what you're aiming for? If it's just low series production of anything, you might still be able to set up a different process that you're comfortable with, no question. But I think that's the potential advantage if you look at this process, at least from a MIM manufacturer's point of view. That's the point. If you set up this whole production anywhere from on a green grass field, whatever, perhaps that's not your concern, but it may be a point to consider when you already are in metal injection molding.
Great, thank you, Sebastian. Okay, another great question here. I'll send this one to you, Lasse. How would someone go about ensuring their mold is robust enough to withstand the forces during injection molding?
Well, I think our standard answer to that is use a metal frame. And we generally do not experience mold deformations on a larger scale. This is not to be compared with conventional metal tooling in the sense that we have a rigid material. But if you encase your printed tool in a metal frame, you will get to a pretty non-compressible situation. That's also what allows us to do complex stuff like what Sebastian has been showing today. We can use FEA, we also do use mold flow, but usually, don't get me wrong, we just try. Because the cost of trial is lower than the cost of having a specialized engineer doing an FEA study. We can get a long way by simply printing a couple of tools and shooting them. I hope that answers the question on a practical level, at least.
Oh, thank you. I think that's great. Okay. This one's another great one. Have you seen any attempts to use 3D printed to create supports made of investment material that could be used during the sintering process? Sebastian, would you like to take that one?
I mean, that's something that we often do in metal binder jetting, actually. That's what is called a life setter, where you basically also take some of the friction forces that the parts get during the sintering when they shrink, and they're on a plate that does not shrink. So you can imagine if you have a part with a very large bottom surface that's on the plate, that if it shrinks, it may get this, you know, elephant foot syndrome. And to prevent this, you can use a similarly printed disc or whatever. It may also be complexly shaped to your part, and then shrink with it, and take over a lot of this distortion due to the friction or during the shrinking process. But this is a general concept, and this can be applied as well here. Usually you try to avoid as much as possible, because you create a second part that you will not be able to reuse. I mean, of course, this can go into general recycling, but of course, trying to be able to, or being able to prevent this as much as possible is a good thing. So if you can introduce this deformation into your as a pre-deformation of your part, which is done by some simulation tools from other companies, this is actually a quite interesting approach. So basically pre-deforming your part so that when it shrinks, this elephant foot does not occur, but it basically gets into the right shape that you want to have. And this is then, of course, easily done when you can print a lot of parts or make them by film easily, because it's fast, and then you can really iron this out on an iterative development basis.
Great. Okay. Let me see. Got a couple more. I know we're running out of time. I'm going to end with one last question for Sebastian here, and that would be. Sorry, 1 second here. My screen has gone dark. Oh, there we go. Okay. What do you see as the key difference between freeform injection molding and other prototyping technologies that you've tried?
Well, I think many, not all of the other technologies, of course, are the green parts that are then used for sintering are made in a layer-by-layer fashion. And there are some technologies that do not show any issues, but many have some anisotropic behavior in shrinkage of the parts. So this is one of the interesting points, because the injection is still done with your feedstock, and so you don't have this issue. You don't have any different shrinkage in X, Y, and Z direction, because basically this isn't there. This is a key feature, and the other one I already mentioned is that if you already have this material and produce with it, you can use it for prototyping and small series, and so don't have to adapt a lot of the or anything of the following process, except for that you have to print these parts, put it in an injection molding machine, and demold the parts. But after that, you can use your standardized production path that you use. And this is, I think, a very unique feature of this concept of freeform injection molding.
Awesome, thank you. I know this brings us to the top of the hour. So before closing out, I'm just going to let everyone know this this webinar will be made available on demand. So if you want to revisit the webinar or any of its content, you'll be able to do so. We should have an email out sometime tomorrow with the link to that recording, and feel free to share it with any colleagues, associates, or friends that you think might be interested. And lastly, if we did not get to your question today, we'll be sure to reach out individually to make sure that your question's been answered. I want to thank everyone for joining us today, and thank you to Lasse and Sebastian for some really great, compelling content. So I thank you for your time and your insight here. I know I learned a lot, so I hope our audience did as well. I hope you all have a wonderful weekend, and we'll be talking soon. Thank you.
Thank you. See you.
See you. Bye.
Bye-bye.